Good day to everyone. So in the last video, we have discussed about the center of gravity and center of pressure, and we have derived the equations for derived the equations for the finding the center of pressure and the center of gravity. So this video, we are going to find out the center of pressure of a rectangular lamina, which is actually immersed in the liquid, as well as we have another geometry, which is triangle, and we are going to find out the center of pressure of this both geometries. So first we are going to looking into the center of pressure of a triangle, sorry, of a rectangle. So in order to find the center of pressure of a rectangle, we are actually taking the rectangular lamina, which is actually immersed in vertically in the liquid, with one edge of the surface is on this liquid. So we consider this xy is the surface of the liquid, and the ABCD is the triangle which we have, the rectangle which we have considered is having the length of B and the breadth of A, and you have considered AB is nothing but the A, and this AD and the BC is actually equal to the breadth, the length B. So if you divide this rectangle in the center of the point, so there is a E of actually cutting this point at the middle of this rectangle. And if you want to find out the center of pressure of this rectangle, so we have to consider a small strip of the rectangle with a small piece which is having the thickness of dx, and this slice is actually situated from this the surface of the water is actually distance is dx. So we are going to find out the thrust acting on this small strip due to this water, due to the liquid, as well as the moment of thrust about the water surface xy. So we are going to find that, and then we are going to integrate that to the whole rectangle. Sorry, that whole rectangle. So if you want to write the thrust acting on this small stripe, it can be written as thrust acting on the strip, which can be written as the h into times of rho times of g. H is the distance, that means we can take it, the x is the distance, into rho is the density of the fluid we have considered, and the g is the acceleration due to gravity. So this is the thrust acting on this strip, so which can be multiplied by the total area. So we can see this area is nothing but the breadth into the height, so a into dx. So the area is a into dx. So I can write this as x rho g into a into dx. So this is the thrust which is acting on the on the strip. Suppose if you want to find out the total thrust acting on the whole rectangle, then you have to integrate this equation from 0 to b, because this is the length of the rectangle, so that I can find the total thrust on all the strips which we have. So that I can just integrate this equation from the limit of 0 to b, the 0 to b, x into rho g a into dx. So that is the total thrust acting on the strip, the entire rectangle. So using this equation, the thrust acting on the strip, I can find out that the moment of the strip due to this liquid, I can find out the moment of the strip, moment of the thrust. So moment of the thrust about the layer of the liquid, the surface of the liquid, which is equal to the total thrust into multiplied by the total height. So I can write it as x times of rho g a into dx multiplied by the distance x, which can be written as x squared rho g into a into dx. So this is the total, the resultant moment of the thrust, the moment of the thrust acting on the surface of the liquid, and this is the moment of the thrust. So if you want to find out the total moment of the thrust of this rectangle, then again you can integrate this this equation from the limits of 0 to b, so that the total moment of thrust, which can be so the total moment of thrust which can be written as integration of 0 to b x squared rho times of ga into dx. And suppose if you consider any point, suppose if you consider this is the point of center of pressure of this rectangle P, which is actually situated from the height of h. Just assuming that this is the point, center of pressure point, and which is actually situated from this water level, this is the fluid level, the height is actually taken as h. Then we can write the total moment of the resultant thrust can be written as the moment of the resultant thrust, moment of the total thrust, total about the surface of the liquid, which can be written as the integration of 0 to b the total the fourth thrust x squared rho times of g a into ds multiplied by the total height, then the height of the point which is we have considered. So I can just write it as h, where the h is the depth of the center of pressure below this surface, the water surface. Suppose at any equilibrium point, this the total thrust of all the strips which is equal to this moment of the total thrust. Sorry, the moment of the total thrust is not x squared, it is actually x into rho gx, because this is the total thrust of all the strips, and we are considering the center of pressure P, which is actually situated at the height of h. So that this total thrust into the height h, which is given the total thrust about the surface. Therefore, I can just equate these two equations. The total moment of the thrust and moment of the resultant thrust can be equated, so that I can just equating these two equations, h times of integration 0 to b x rho ga into dx, which is equal to this integration of 0 to b x squared rho g a into dx, and in both sides rho into g into a is a constant, so that I can take it outside. So h into rho g a integration of 0 to b x into dx into dA, which is equal to rho into ga integration of x squared into dx, so that I can cancel out all these constants in both the left hand side and right hand side, so that h into I can just integrate this with respect to x, so that I will get the x squared divided by 2, and if you substitute the values of limits, I can get b squared divided by 2 in the left hand side, which is equal to, here you get the x cubed divided by 3, and again if you substitute the values of limits, you get b cubed divided by 3. So from this equation I can find out the h, the height of the point where the center of pressure is actually situated, which is equal to b cubed divided by 3 into 2 times of 2 divided by b squared, so that this will cancel. The final value of h is equal to 2 divided by 3 times of b. So this is the height of the center of pressure of the rectangle or rectangular bar or rectangular lamina, and the thrust of the every elementary strip acting on the midpoint of this any geometrical object, so that the center of pressure is actually like lying in this point E and F, anywhere in this point E and F, which is the midpoint of the rectangular bar. Okay, so now we have found the center of pressure of the rectangular ball, which is h is equal to 2 divided by 3 into b. Okay, so next we are going to find out the center of pressure of the triangular lamina. So in order to find out the triangular lamina, suppose if you consider this is a triangle, suppose if this is actually immersed in the water, so we can consider two cases. Either this vertex of the triangle is actually on the surface of the liquid, or in opposite direction. That means the the one side of the triangle is actually on the surface of the liquid. So we are going to consider the two cases where the vertex is actually on the surface, or the one of the sides of the triangle is on the surface. So first we are going to find out the center of pressure of the triangular lamina, which is immersed vertically in a liquid with its vertex in the surface of the liquid, and the base is in the horizontal with the liquid surface. So we are going to consider the triangle ABC, which is actually immersed vertically in the liquid with the vertex A is on the surface of the liquid, with its base BC is actually horizontal with the liquid surface. So we have considered this BC, the length of the BC is actually taken as a, and the depth of the base of the lamina B is actually taken as a B from the liquid surface. Suppose if you divide this triangle into small pieces, small elementary stripes, which is having the thickness of dx in parallel to the bottom surface BC, then consider the one of the small strips which is taken as a B1 and C1, which is actually situated from this liquid surface is taken as the distance is actually taken as x from the water surface xy. Then we can find out the area of this small strip as, so the area of the small strip B1 C1, which can be written as the total length B1 into C1 into the thickness dx. So that I can write it as B1 C1 into dx. Actually, if you consider the B1 and C1, this length of the B1 and C1 is actually vary with respect to this height B, so that I can write the B1 and C1 as a times of x divided by b into dx. So this is the B1 C1 is given by a divided by b into x. So that is this is the total area of the small strip which we have considered. So once we know the area, then we can find out the thrust on the strip, which can be equal to the strip B1 C1, which can be written as h times the height into rho into g into the total area. The height is nothing but the total distance x, so that x into rho into g into the area. So a x divided by b into dx, or I can rewrite this as x squared rho g into a divided by b into dx. So this is the thrust on the strip. The thrust of the strip in the B1 C1 due to this liquid presence in this above the liquid surface, means above the B1 C1 strip. Now we can find out the moment of this thrust about the liquid surface on this strip can be written as, so the moment of this thrust about the surface can be written as this total thrust into the thrust we have considered multiplied by the distance x, so that I can write this as a x cube rho into g a divided by b into dx. So we have found that the thrust of the strip as well as the moment of the thrust actually acting on this stripe due to the water surface. Now we can just find out the total thrust of the strip. I mean the total thrust on the entire triangle just by integrating this equation in the limits of from 0 to b, so that the total thrust on all the strips which can be written as integration of value from 0 to b and s squared rho g a divided b into dx. Similarly, the total moment on the entire triangle can be written as the total moment of the thrust of all the strips which can be written as, again, the integration of 0 to b x cube rho g times of a divided by dx. Okay, so suppose we are integrating these two equations as a function of the limit 0 to b. so that we can found the total thrust of all the strips as well as the total moment of the thrust of all the strips in the limitation of 0 to b. So again, what I'm going to consider is I'm going to again consider a small point P, which is actually assumed as the center of pressure of the triangle. So which is actually situated in the midpoint of the point AD, because the center of gravity is always acting on this midpoint of the triangle. Of any point in this, any point lies between this A to D. Suppose if I going to consider the point P in this triangle, which is the center of pressure acting on the triangle, and the distance from the water surface can be taken as a h. Therefore, the moment of the thrust acting on this point P, which is actually situated from this water surface xy, can be written as, so the moment of the resultant thrust, total thrust, about the surface, the liquid surface, which can be written as the total thrust into multiplied by the h, so that h times of integration of 0 to b x square rho g a divided by b into dx. Yes, I already told you that the h is the depth of the center of pressure below the water surface xy. Okay. So since the two moments are equal, so I can equate this equation and this equation here, so that I can write h times of 0 to b x square rho g a divided by b into dx, which is equal to the total moment. Sorry, not this one. So this one, the total moment, integration of 0 to b x cube rho g a divided by b into dx. So as usual, I can take the constants outside, h into rho g a divided by b and 0 to b x square dx. Similarly, the right hand side, rho g a divided by b into the multiplied by the integration of 0 to b x cube into dx. So I cancelled out all the constant values both left hand side, right hand side, and then if you integrate the equations based on the integrate this part x squared dx and the in the right hand side x cube dx, we get the x h into, this is x cube divided by 3, x cube divided by 3 will get, so if we substitute the values of b, so b cube divided by 3, which is equal to here b power 4 divided by 4. Therefore, from this equation, I can easily calculate the height, h is equal to b power 4 divided by 4 into 3 times of b cube. So this b cube and b can get cancelled. So 3 by 4 times of b, that is the value of h. So the center of pressure of the triangle, which is the vertex is actually immersed on the surface of the liquid. Then the center of pressure is actually lies in the 3 by 4 times of this the height b from the water surface. Okay. So this is the expression. So using this expression, you can easily calculate the center of pressure, the point of the pressure, center of pressure of the triangular lamina, which is immersed vertically in a liquid with its vertex on the surface. So next we are going to consider another case, the center of pressure of the triangular lamina, where the one side of the triangle is actually immersed on the surface, and the vertex is actually immersed on the liquid. That is exactly opposite to this present case which we have considered. So now we have considered this triangular lamina, which is the one side of the liquid, one side of the lamina is actually immersed on the side of the surface, and the vertex is actually inside the liquid. And we are going to find out the center of pressure. And in this case, as we said, we have going to again consider the same triangular lamina ABC, and the length BC is actually taken as A, which is actually on the in the surface of the liquid, and this AD is the midpoint of this triangle, and the B is the total, the depth of the vertex from the liquid surface. Suppose if you again divide the triangular into a number of elementary small stripes with a smallest with a thickness of dx, with a parallel with the surface BC, and we are going to consider one of the stripe which is actually situated from this liquid surface with the distance of x, and the name is B1 and C1, so that we can again find out the area of the strip, which is different from the earlier we have calculated. The area of the strip of B1 C1, which is equal to B1 C1 into dx. So here we can see that B1 C1 is actually situated in the distance of b minus x, so that I can write this as b minus x divided by b whole into dx, because the length of this thickness will vary with respect to the b, so that I can write the area of thickness as b minus x divided by b into the thickness dx. So this is the area of the strip, so that I can easily find out the thrust acting on the strip, which can be equal to the distance, that is x, into the density of the liquid, the acceleration due to gravity, into the area b minus x divided by b into dx. So if the thrust is known, then we can easily find out the moment of the thrust about the liquid surface, so that the moment of the thrust about the surface, which can be written as the thrust into the distance, height h, that I can write it as x squared rho g into b minus x divided by b into dx. So I know the thrust acting on the strip as well as the moment of the thrust about the surface, so that I can calculate the thrust as well as the moment of the entire triangle, so that I can just integrate these two equations as with respect to the limit of 0 to b. Therefore, the total thrust on all the strips can be written as integration of 0 to b this x rho g into b minus x divided by b into dx. Similarly, I can find out the total moment of the thrust on all the strips, which is equal to integration of 0 to b in this equation x squared rho g into b minus x divided by b into dx. So again, what I'm going to do is I'm going to again consider the one of the point here, then maybe the point P, which is we can considering as a center of pressure, which is actually situated at the median of the triangle which line the AD, and the height between this from the water surface taken as a h. Then I can find out that the total moment which is acting on this corresponding center of pressure point P, that is the moment of the total thrust acting on this point P due to this the surface xy, can be written as the moment of the thrust, the resultant thrust, the total thrust about the surface this is equal to the total thrust multiplied by the height h, so that I can write as h times of 0 to b x rho g b minus x divided by b into dx. Now I can equate this total the two total moments of the triangle, so that I can equate these two equations, h into 0 to b x rho g b minus x divided by b into dx, which is equal to integration of over the limits 0 to b x squared rho g into b minus x divided by b into dx. If I take the constants outside, then h into rho g divided by b integration of 0 to b x into b minus x into dx, this is equal to rho g divided by b integration of 0 to b x squared b minus x into dx. so the constants will get cancelled out each left hand side as well as right hand side. So I can write this expression as h into integration of 0 to b x into b minus x squared into dx, which is equal to integration of 0 to b x squared b minus x cube into dx. Now if you integrate this equation, I will get h times of this is x squared divided by 2 times of b minus x cube divided by 3 times of integration 0 to b. Again here you get x cube divided by 3 b minus x power 4 divided by 4 into with the limits of 0 to b. So if I apply the limit, I get h times of b cube divided by 3 minus b cube divided by 2 and b cube divided by 3. Here the right hand side you'll get b cube divided by 3 minus b power 4 divided by 4. Now if you take the LCM of this both the sides of this expression, then the final value will be equal to h times of b cube divided by 6, which is equal to b power 4 divided by 12. B power 4 divided by 12. So from this equation I can easily calculate the center of pressure height, h is equal to b power 4 divided by 12 into 6 times of b cube. So this will get 3 times, and so we'll get h is equal to b divided by 2. Therefore the center of pressure is on the median of the AD at the depth of b by 2 times from the surface, liquid surface x and y. Therefore the center of pressure of the rectangular lamina is equal to 2 by 3 times of b, and for the center of pressure of the triangular lamina with its vertex is on the liquid surface, which is equal to 3 by 4 times of b, and finally the center of pressure of the triangular lamina with its one side of the surface is on the surface of the liquid, which is equal to b divided by 2. So using this formula, we can easily find out the center of pressure of the geometry is rectangle as well as the triangle in the given liquid. Okay, so I stop here. Suppose if you have any doubt, then we can discuss in the online class. Okay, thank you.